All right, so what happens if a patient gets too little anesthesia? Yeah, wake up during surgery. Absolute nightmare. What about too much? Yeah, you could die. Or it could cause damage to your organs. There's lots of things that can happen. So it's a delicate balance. So we're going to skip 2A and just go to 2B. So you could have looked at the graph. The graph wouldn't give you like the best answer, but it gives you something really close. Or you could plug in 0.5 or 1/2 into the calculator. What did you guys get? 2.8%. All right. So what about 24 hours after the surgery? 1.443%. So even a whole day later, there's still some anesthesia in your body. 48 hours later, there's still some anesthesia in your body. But eventually, actually, hold on, we're not there yet. So on number 3, for the anesthesia to be considered effective, the concentration needs to be at or above 5%. So these numbers are percentages. So you could look at the calculator, but you could also just look at the graph. And so how long should the anesthesiologist wait, or the surgeon wait? 1 hour. And then how many hours is the anesthesia effective? 5 hours. Good. All right. And then number 4, what what I was about to say after C. But after many, many hours, what would you expect the concentration to go to? 0%. And so I'm going to write that as a limit. They didn't ask you to do that. But if time is after many, many hours, what would time be approaching? Infinity. SCOT. In this case is going to be 0. That limit as t approaches infinity or x approaches infinity is what we've done before for in behavior. So we're going to do that again today. All right, and then for 5, for large values of t, which grows faster, the numerator or denominator? What do y'all think? Denominator, because the t is being squared. It has a higher degree. So today we are going to kind of look at which is going to dominate the numbers as you get really, really big and as you get really, really small. In the middle, the smaller numbers, they both affect it. And so the graph can do all kinds of different squiggles that as you get really, really big, whichever one has the larger degree is going to be the one that dominates. All right, and then on this last question, it's kind of hard to understand what it's saying, but if you take a regular size number and divide by a huge number, do you guys know what you get? Nobody knows this. I don't know why it surprises me, but my last class didn't know it either. So if I took like 2 and I divided it by 900 million. So you're taking 2 and dividing it into 900 million even pieces. What size would those pieces be? It would basically not exist, so it would be 0. So if you take a regular number and divide by infinity, that's going to be 0. And that's kind of what happens when the denominator dominates. You're taking a really big number and raising it to a power. So it's going to end up, when you divide by that infinity, you're going to end up with 0. All right, so let's go to the notes. And the 2 things we're going to talk about today are horizontal asymptotes, which is what you just found. Did anybody here wrote it? Sorry. Trying to save time. I missed it.
Oh, we got some.
All right, so a horizontal asymptote is what you found when you did that. It eventually is going to go to 0 question. So a horizontal asymptote is a horizontal line the graph approaches as x approaches infinity and negative infinity. So as you go to the far, far ends of the graph, the graph levels off at a horizontal line. That's a horizontal asymptote. And to find horizontal asymptotes, you're going to compare the degrees of the numerator and the denominator. So anytime I'm doing n of x, here is numerator, d of x is denominator. Right, so there's three different situations. So horizontal asymptotes has a lot you have to remember. So this is something, before we take our test on this, like it'll be later next week, something you're probably going to have to study and look back over. But if the numerator degree is less than the denominator degree, like what we had on the anesthesia problem, then that means the denominator dominates. So you have that situation where you're dividing by infinity. And anytime that happens, the horizontal asymptote is y equals 0. So every single time you have this rational function and the numerator degree is less than the denominator degree, y equals 0 is your horizontal asymptote. And when you describe your end behavior, it's just going to approach that horizontal asymptote. So both of those are going to be zeros. All right, and then if they have equal degrees, the degree of the numerator equals the denominator, then neither are going to dominate. But there is still a horizontal asymptote. So it's y equals this long fraction. And what you get for the horizontal asymptote is the leading coefficient of the numerator. So we'll do n of x. There's barely enough room to write all this on your space I gave you. Over the leading coefficient of the denominator. Okay, so that just ends up giving you a number like 4/5 or 1/2 or 3. And that will be your horizontal asymptote, and also you use that to describe your end behavior. So I'm just going to do LC for leading coefficient of the numerator, just so we don't have to write it all out again. All right, and then the last situation is when the degree of the numerator is the greater one. It's the one that dominates. And whenever the numerator dominates, it never levels off. It's just going to either keep getting bigger and bigger and bigger. Oh, I didn't mean to write the dominates. Sorry. So the top is dominating, then it's getting bigger and bigger and bigger faster than the denominator is. And so there is not going to be a horizontal asymptote. It's never going to level off at a horizontal line. And so for your end behavior, it's going to either be infinity or negative infinity. Right, and to figure out which is which, we're going to have to further investigate. So we must further investigate. right. So that further investigation. So we're going to determine the end behavior when the numerator dominates. What we'll do is analyze a simpler function given by the ratio of the first terms of the numerator and denominator. Now, those first terms, the numerator and denominator, need to be in order. So I don't think there's one on our examples. There's definitely one on our homework. We have to pay attention to the order. All right. So for these examples, we have two where the numerator degree is larger than the denominator. So the numerator is dominating. And so we're going to say that the ends act like a function we would get if we just divided those first terms. All right, now we do need to simplify this down. So 3 divided by -6 will get -1/2. And then to divide x to the fifth and x squared, what do I do with those powers? Subtract them. So it's going to be x to the third. Now I'm asking you to remember a lot of stuff from either last year in Algebra 2 or from last week when we talked about the end behavior of things like this. This is going to act like a cubic function. And so how do I figure out what's happening on the right side by looking at the function? The leading coefficient. And so if that leading coefficient is negative, the right side is going to be negative infinity. And how do you figure out the left side? Right. So you look at the degree. It's an odd degree, so the left side is going to do the opposite. Okay, we're going to do one more like this, and then we'll just practice it all. So this one, the numerator dominates. So the ends act like a different function where I'm just going to divide those two. X to the fifth divided by x cubed, or y equals x squared. Now, I really hope you guys in your brain can visualize what y equals x squared looks like, because it's a parent function. Nothing weird's happening with it. What does that graph look like? A parabola, right? Just the parent function parabola. And so if you can visualize what the function looks like, you can go ahead and say, without like going through the rules, what's happening at the ends. They're both pointing up because you know what a parabola looks like. Now, if there's negatives with it or numbers, you have to think about it a little bit more, but that one's not too bad. All right, so on these three examples, we are going to find the horizontal asymptote if it exists. If it doesn't exist, we're going to explain why, and then we're going to describe the end behavior. Okay, so I'm looking at the I'm looking at the degrees. What do you notice? They're the same. And when the degrees are the same, that's where you do leading coefficient over leading coefficient. So y equals 3 over 2. And if there is a horizontal asymptote, that is just bring that over, and that describes your end behavior. All right. And then for B, if we look at the degrees, the numerator is less than the denominator. So that's like the one with the anesthesia. So what would the horizontal asymptote be? 0. Good. So then these are both 0. All right. And then this last one, the numerator is greater. So what does that mean about the horizontal asymptote? There's not going to be one. It doesn't exist. And it doesn't exist because the numerator dominates. So it's either on one side going to keep getting bigger and bigger and bigger, or smaller and smaller and smaller. But we can still give the end behavior. So the ends are going to act like y equals x squared over x. So what do you get when you divide x squared by x? X. All right, so you guys think about what y equals x looks like, or use the rules for end behavior of polynomials and see what you can fill in for these two on your own. So y equals x is also a parent function that has a slope of 1 and an intercept of 0. And so on the right side, we're pointing up, and on the left side, we're pointing down. Or you can just use the rules where there's a positive leading coefficient, so that's positive. There's an odd degree, so that's going to be opposite. Either way, as long as you know a way, I'm fine. Okay, couple more. On number 2, we're going to write our own function that has this end behavior. So anytime you, on a rational function, I should say, it does say rational function, if it tells you that the limit as x approaches infinity is this number, what it's telling you is the horizontal asymptote is y equals 4/5. And so we want to write our own function, and we could all write different functions if we wanted to, that when I find the horizontal asymptote, I get 4/5. So which situation are we going to have to use out of these three? Same degree, right? And so they're going to have the same degree, and your leading coefficient on the numerator needs to be 4, and your denominator needs to be 5. All right, so and they need to have the same degree. So what degree do you guys want? It could be anything you want. 2? Okay, so we have 2, 2. And then after that, it also, as long as your degrees are smaller, it can be anything. So I'm just making stuff up. That is an equation. It doesn't have to be, it's obviously not the only. All right, and then population increasing and stuff, especially with animals or insects in this case, is a really common rational function application. So a rare species of insects was discovered in the Amazon rainforest. To protect the species from extinction, entomologists transferred a certain number of insects to a protected area. The population P of the new colony T days after the transfer is given by this function. And so A asks us to find the y-intercepts. Now, we didn't talk about y-intercepts today, but we have talked about them before. And anytime you want to find the y-intercept of any function, you just put 0 in for x, or t in this case. So anything that has a t becomes 0, so it disappears. So what does that leave us for our y-intercepts? 25. Good. So what does that mean in this problem about insects and the colony size? What is the time? 0. So this is going to be the initial. Very good. The initial amount of insects is 25. Or Initially, 25 insects were transferred to the protected area. However you want to word it, but it's when time is 0. You with me, Derek? All right. All right, and then for letter B, we want to find P of 5. So we'll just take that 5 and we're going to put it in for T. And I'll go ahead and tell you, because I know you guys can do this, that you get 85.366. Okay, so how do you interpret this in the context of the problem about insects? So 5 days after the transfer, there were about, now we're not going to do a partial insect, so 85 insects in the colony. All right, and then C asks us to find the limit as t approaches infinity of P of t and interpret the answer in the context of the problem. All right, so if we're talking about rational functions and you see this, what are you going to think? What are they asking you to find? Horizontal asymptote. All right, and when we're finding the horizontal asymptote of a rational function, we're going to compare the degrees of the numerator and denominator. So be careful. This one is out of order. So when we're comparing the degrees, these are the two we're looking at. What do you notice about their degrees? They are the same. So when you're doing the horizontal asymptote with the same degree, we're going to do the leading coefficient, which means the coefficient of that value we were just looking at, that term, divided by the other one. And that is going to give you 2,500. All right, so what does this mean in the context of the problem? Right, have you guys in biology, did you study carrying capacity? Some people say yes and some people say no. So that's like the environment will only support this amount of insects. So we can word this ton of ways. I'm going to say after many days, the population of insects will level off at 2,500. All right, and then on number 4, this is a 1, or this is 1 where the numerator is dominating, and so the end behavior is going to act like which one of these? Do you guys think? D. Yeah. We just divide those two, and we're going to get D. All right. So what questions do you guys have? I know it's been a lot these last 5 days, or the last few days. All right. Let me give you your assignment.